A very good afternoon and a warm welcome to you all. Requesting everyone to please take their seats as we are about to begin.
ये फॉर्मेट है, ये देखो डबल दोनों एक साथ रिकॉर्ड होगा, सेम साथ नहीं होना चाहिए ना। हाँ, और
This session, Base Load Clean Energy, Coal Plant Reuse and Industrial Heat, the first session of our SCALE conference. It's my honor to welcome our session chair, Mr. P.K. Gupta, GM Energy Transition, NTPC. Thank you, Mr. Gupta, for joining us. Shri Pankaj Kumar Gupta is a mechanical engineering professional with more than 31 years experience in thermal power plant in the area of engineering and operation and maintenance of steam generator. Out of which more than 25 years of experience in engineering and design of subcritical and supercritical steam generators and its auxiliaries. He was involved in the preparation of tender documents for steam generator ESP packages for the power plants ranging 200 megawatts to 800 megawatts. He is primarily involved in all SCR, SNCR pilot tests being done in NTPC. He is also having 5 years of experience of operation and commissioning of thermal power plants, specifically in steam generator area. We welcome you, sir, as session chair. I'm going to request Rohan from Spectrum to please share with Sir a little sapling as a token of appreciation. Thank you very much. I would now like to invite all our speakers to kindly join us on the desk. Mr. James Bentetos from Quest, Mr. Marcus Lisman from GTI SCO2, Mr. Jan Korkov, Mr. Suhas Bakshi, Mr. Rajesh Ayyapasu, and Mr. Ranjit Manikar. I will now request our session chair to please hand over the wonderful saplings to all our speakers. As we're running out of time, we're going to just quickly move ahead with our speakers taking over. And I'm going to request Mr. P.K. Gupta to please take over first, then we hand over to our speakers.
Hello, so namaskar, good afternoon, and I welcome everyone in this session. So first I welcome to my speakers. So in this session there are 6 speakers. I know the afternoon session is very most difficult session because after having a good lunch, so that session is very difficult. So now before starting, I wanted to say some few words that I am working in NTPC, and you may be knowing NTPC is a very largest company and has installed capacity about 75 gigawatt in terms of the, and mostly which is the coal predominant fuel as on date. And now to strengthening our core business, we have diversified our portfolio across various sectors, including coal mining, hydro, renewable, consultancy, power trading, green hydrogen mobility, and so on. So that we wanted to become an integrated energy company. Basically, I am an NTPC. We are a electron moving company, and for that the energy is required, which can come from coal or from any source. So that is the idea, and presently, in terms of the India, we have 17% in terms of the installed capacity, and we are generating 25%. That means in every 4 bulb, NTPC is having the lighting the 1 bulb out of 4. So that means 25 contribution of the NTPC. And earlier power plant was process industry. Now day by day, because of the development, now power plant also become a chemical company, industry. So now we are dealing with the ammonia, then methanol, ethanol, etc. NTPC is also taking various steps for making its portfolio greener by adding significant capacity of RE by 2032. Our company planned that 60 gigawatt capacity addition of the RE sources. In this session, we have 6 presentations, and I will tell this is very important session because topic of the session is very relevant in present context. And I will tell you why. Because everyone wants that green power and 24/7, which is and then because of energy transition and decarbonization, which is the need of hour, we have to meet the global climate target. However, for a country like India, where per capita energy consumption is fraction of global average, and we require energy security, sustainability, and affordability major factor here. And solar and wind, which consist major part of the RE, but highly variable in nature. So, in India, we have to understand that the source of energy available in India only as we don't have a gas. And nuclear and hydro, as we are discussing in the morning, which have the long gestation period, but also having the many challenges. So it is very important to balance the power. For balancing power in India, coal is the major source for energy. And coal is also having some challenges, and for balancing the grid is also the problem. So that means we require a RE, which people in the session will cover, and which will we want that 24/7 the power. That is the important thing. And coal, now we are giving the cleaner power, because of the new environment norms, we have now reduced the many things like SOx, NOx, SPM, mercury. But we still need the green power. So for green power, we require that how we can include the various fuels like biomass and then maybe ammonia, hydrogen, methanol, etc. So in this session, as we have this energy which is not wind or that solar, but we have geothermal, wave energy, ocean energy, bioenergy, or like supercritical CO2. So this is the need of hour. So this session is very important. I think now we will call one by one, but I request every speaker, because of the time constraint, kindly restrict up to 10 minutes. And we will take the question answer session after the completion of this session, at the end of the session. Okay, so I think first I call Quest Energy, who is making basically the drilling technology for making the geothermal. So I request Mr. James Benesetos, who is the head of business development at Quest, and to make their presentation and kindly make brief and 10 minutes. Okay.
Hi, it's nice to be here today. First time in India, so I'm very happy to be here. My name is James Benetatos. I lead the business development team at Quaise Energy. So Quaise is commercializing a revolutionary drilling technology to enable access to a global energy source that is available everywhere on Earth. It's more abundant than fossil fuels, and it has the economics at the same scale of the current renewable technologies. This energy source is geothermal energy. Quaise is reusing fusion technology, or a technology that was developed for the fusion industry, and repurposing that technology in order to drill wells deep into the earth to unlock heat 8 to 12 kilometers deep. We're talking about temperatures in the 400 degrees Celsius region. When we're able to reach these depths and temperatures, we're able to generate power at the scale of the fossil fuel industry, the scale that the fossil fuel industry currently does. By reaching temperatures of 400 degrees Celsius, we're able to drill a set of wells that can produce 25 to 30 megawatts electric. With multiple wells, we would be able to go alongside a coal-fired or natural gas-fired power plant and drill enough wells to totally replace that generation. By leveraging the supply chain and workforce of the oil and gas industry, Quaise will be able to generate enough clean power to meet our energy needs for 2050. Now I just want to give you a little bit of background on Quaise and where we've been and where we're going. So the company was started in actually 2007 at MIT. There was a professor there that was doing research in fusion and decided to try to drill some wells, drill through rock using a beam of energy. In 2018, our company was spun out, and since then, in the 6 years we've been a company, we've 100x the results of MIT. And in the next few months, we're going to be taking those results and bringing them out into the field, where we'll be drilling 1 kilometer well through solid granite rock using our microwave technology. From there, we will move to a geothermal scale pilot in Bend, Oregon, where there's a volcano. And once we've proven that we can do this at the geothermal scale, we'll be looking to repower the first coal-fired power plant. We'll be looking to do that in the western United States. So we are developing a drilling technology, but I understand geothermal could be new to India, so I wanted to start with what is geothermal energy. So geothermal energy traditionally is the confluence of heat, water, and permeability close to the surface. It's usually accessible with conventional drilling technologies. These anomalies don't really exist in India, but if you were to drill deep enough in India and other parts of the world, you would be able to reach these temperatures that we need for power generation. So by creating an engineered geothermal system where we drill a set of wells and use rock fracturing techniques to connect them together, we can produce geothermal anywhere in the world. The key is to get deep enough. So the way this works is you drill your first injection well. You fracture it using thermal or hydraulic techniques. You then drill a production well to connect the two wells, and then your system is operational. To operate the system, you flow water down your injection well. It extracts the heat from the rock, and then in its less dense phase, will flow up the production well. At the surface, you can use a heat exchanger to transfer that fluid to a clean, pure water, and then that water will flash and expand through a turbine to generate electricity. The key here, though, is to get deep enough. So how do we get deep enough to access these temperatures? That lies in what Quaise is doing in its drilling technology. We are repurposing the gyrotron, which is the device from the fusion industry. It's what the fusion industry uses to heat their plasma to 150 million degrees Celsius. We're using this to vaporize rock to drill into the earth. The gyrotron is a device that stays at the surface. Its input is electricity, and the output is electromagnetic radiation in the form of millimeter waves. The millimeter waves are carried away from the gyrotron through a waveguide, which is simply just a metallic pipe, and carried downhole to the rock face. The waves are then dielectrically coupled with the rock. This is the same principle as heating food in your microwave oven. The dielectric heating causes the rock to rapidly heat past its melting temperature, and it's actually vaporized. The rock is then carried out of the hole via a purge gas that we inject in the waveguide with the millimeter waves. The millimeter waves and the purge gas don't interact, and we're able to flush out the rock out of the hole and be able to continue drilling to depths 8 to 10 kilometers. For our first couple of pilots, we do aim to reach depths up to 20 kilometers when we are a mature company. The key, though, is really temperature. It's the temperature that we're trying to get to, which is a function of depth. So what are the advantages of millimeter wave drilling over conventional drilling technology? So Quaise's drilling technology is more simple than conventional drilling. There's no tools or anything downhole that can wear out. We simply have a pipe. So when you're drilling conventionally, your drill bit tends to wear out every 200 to 300 meters. Then you have to pull out your entire drill string to change the bit and then go back in to continue drilling. This is also amplified with heat and depth, and the drill bit wears out faster. So as you drill deeper, your economics increase exponentially. With millimeter wave drilling, we're able to drill at a constant rate of penetration of 3 to 5 meters per hour, and nothing there to wear out. So with the combination of being faster and being simpler, we arrive at the fact that millimeter wave drilling is cheaper than conventional drilling, and it allows us to get to the depths that we need to get to. This drilling technology will enable LCOEs in the range of $60 to $80 per megawatt hour, with costs only going above $80 per megawatt hour in regions of the world where the geothermal gradient is well below average. So what are the uses besides electricity, and how can this fit into the Indian ecosystem? We could use geothermal heat for both industrial heating and electricity. We can co-locate geothermal power plants with paper and pulp facilities, chemical manufacturing plants, recycling, and many other processes that use heat with temperatures less than 400 degrees Celsius. And we know that clean electrons are going to be the most important commodity of our generation. And we'd like to partner with utility scale power, direct air capture, clean green hydrogen production, and large industrial processes and data centers to power them with co-location of power. Geothermal energy can also be used as a base load generator, which increases its economics, makes the cost a lot cheaper, but can also be paired with existing renewables, wind and solar, to be a load-following asset to fit into really any generation profile. Again, because we're able to get so deep, we're able to generate electricity at costs of between $60 and $85 per megawatt hour, and with the $60 being high geothermal gradients and the $80 being an average geothermal gradient. And in India, we find that there is plenty of locations that have geothermal gradients between 30 and 40 degrees Celsius. So India would be a prime location for Quaise to install geothermal power plants. And we see that our technology is different from the existing technologies because we don't exhibit exploration risks. We're not looking for a geologic anomaly, so this lowers our costs. Our drilling costs are lower as a package because we don't have the non-productive time that conventional drilling has. And our higher output per well, we're talking the first EGS demonstration in the US is around 2 to 3 megawatts per well, where if we can get to the 10 kilometers, we can do 25 to 30 megawatts per well. Additionally, geothermal is extremely reliable and operates at capacity factors over 90%. Quickly touch on our business model, but we would like to partner with utilities such that we would develop the geothermal well field and the utility or the existing independent power producer can develop and operate the power plant. We as Quaise can do this ourselves, but for the sake of speed, we would like to partner with existing utilities and power producers so that we can develop the well field and move on to the next one and put as many clean electrons on the grid as possible. In conclusion, we are the only solution in the near future that is capable of putting clean electrons on the grid at scale. We have the oil and gas industry that we can leverage, the supply chain and the workforce, so that we can do this rapidly. And we are the only technology that would be able to remove gigatons of CO, or replace gigatons of CO2 worth of fossil fire generation. I thank you for your time today, and I'll be around for questions afterwards.
Hello, thank you very much. It's a very nice presentation, and definitely geothermal is the good technology, and that is 24/7. It can give the 24/7 power. And the major challenges which is related to that drilling, which is already has given solution. So now I will call upon the next speaker from GTI SCO2, Mr. Marcus. So he is Senior Director, Business Development Energy Supply of GTI. I request kindly start your presentation. Thank you. Kindly.
Ladies and gentlemen, we're going to request you to hold on to your questions for all our speakers. We're going to take the Q&A right in the end. So it's a request, please hold on to your questions. Thank you.
Good afternoon, everybody. First of all, I really would like to thank the conference organizers for having us here and for everybody here. Really appreciate the opportunity to present here at scale. Before I talk about the technical aspects here, let me briefly introduce GTI Energy. So GTI Energy is a leading research, development, and training organization. We cover the entire energy value chain, from sourcing energy, making energy, moving energy, storing and utilizing energy. We have a long tradition, especially in gas processing, but I've expanded now into other technology areas, including biomass conversion, gas separation, CO2 capture, combustion, hydrogen production and storage and transport, and utilization. We are a mission-driven organization. What that means is we do take the energy transition seriously. That's really our main focus. And we do believe that the energy transition needs to happen fast, but it also needs to be affordable for the world, and energy supplies do need to be secure. We are based in the Chicago area, about 500 people. Over the last 10 years, we've executed about $1 billion of R&D work, and we do a lot of that work in collaboration with others. So why is CO2 cycle technology important? So CO2 cycles offer really higher efficiency, are more compact and scalable, don't necessarily use water at all in the power cycle, and allow for lower carbon power generation. What's important to understand is these power cycles, the supercritical CO2 power cycle technology, is very versatile in the sense that it can be used with a variety of heat sources. So those heat sources might be heat sources from fossil power generation, conventional heat sources, but also biomass-based heat sources, concentrated solar power, geothermal, in fact, nuclear applications, but they're also good for generating energy storage, and as a first implementation, probably for waste heat recovery. Here we go. So what is supercritical CO2? Just imagine, compared to a conventional steam Rankine cycle, the working fluid is not water or steam, it's CO2. It's CO2 at process conditions that are above supercritical. So what that means is it's a very dense fluid that behaves, has a fluidity of a gas. And what that leads to is actually very high power cycle efficiency. So on the graph in the top right, you see in red the power cycle efficiency for supercritical CO2 applications as a function of turbine inlet temperature. So as you go to higher temperatures, supercritical CO2 power cycles are by nature more efficient than conventional steam Rankine cycles. No phase change occurs in the CO2 power cycle. GTI Energy is leading a project, a pilot project that we call the Supercritical Transformational Electric Power Project, STEP in short. And the scope of this project is design, construct, commission, and operate a 10 megawatt supercritical CO2 pilot test facility. The team here is GTI Energy, as well as with Southwest Research Institute as the host site, General Electric Global Research, or now GE Vernova, as an industrial partner, and then the project is mainly funded by the US Department of Energy. There's also joint industry partners involved, a lot of organizations that have an interest in the advancement of this technology. They include KEPCO from South Korea, EGAT from Thailand, a couple of utilities from the United States, but also other research organizations from around the world, like Enercan in Canada and CSIRO from Australia. So the total investment into this facility has now exceeded $160 million. The objective is really to demonstrate a pathway to a power cycle efficiency that's about 50%. And then also verify the system performance and uploadability. This is a completely new power cycle technology. It has never been shown at this scale before. The facility is also meant to be flexible in the future, so it's pretty spaced out. We'll see that in the next picture. And it allows for other process equipment to be brought into this in the future and to be tested. Here you see the outside of the facility, what it currently looks like. So in the middle, I'll show you a picture from the inside in a minute here. But you see the test facility, you see the heater. This is a gas-fired heater as the heat source for the supercritical CO2, but as I mentioned, it's heat source agnostic. Other heat sources could be used as well. You also see the inventory storage system, as well as an electric load plant. And the facility is producing power, but is not connected to the grid. The load goes actually into the load packs. What you see here is the inside of that facility. So it's completed now. This is the major pieces of equipment. It's the turbine, the bypass compressor. You see the high temperature recuperator there. And also on the top right, the CO2 inventory management system. It's very critical to have that inventory management in the power cycle. On the bottom right, you actually see a group of people. It's good to see that at scale, and they are actually holding a model of the turbine. It's about this big, and that is actually a model of a 10 megawatt turbine. So you see how compact the turbine machinery really is. On the top right here, you see the actual turbine with the person for scale. So this is a 10 megawatt supercritical CO2 turbine, 10 times as compact as a conventional steam turbine. So this turbine can produce 20,000 horsepower. It's rated for 29,000 RPM, so very high power density. So the only other machinery that that exceeds that type of power density are rocket engines. Otherwise, there's nothing else. Some notable achievements really from the technology maturation as we built this facility. Some very unique materials aspects. For example, the turbine stop valve was the world's largest high temperature Haynes 282 casting. Very unique materials. The same also with the high temperature recuperator, world's largest high temperature printed circuit heat exchanger ever accomplished. That was being made in the UK. And I think this is important also in the context here in India. It's not just about the application of this type of technology which can go into many heat sources really for power generation. It's also about the unique materials and the handling, the shaping of those materials, be it valves or be it piping, bending, and those types of materials. There's a lot of knowledge that needs to go into that, and ultimately we see markets and suppliers actually possibly from India to deliver into this emerging technology. I mentioned earlier that we have a joint industry program. So this is really to allow other organizations that have an interest in the development of this technology to participate actively in this program. There's 2 levels of membership in there. Depending on the membership level, people get access to all the data, get access to intellectual property, and have certain rights through that. I mentioned before there's a number of organizations from around the world that have already joined. The program is still open. In fact, we're in discussions that are closing very soon here with a couple of new members, and hopefully we can make some announcements very soon. So in summary, supercritical CO2 power cycles are very versatile. We use in different heat sources and provide costs and performance benefits. The technology maturation by the STEP project will provide a path to future commercial systems with higher efficiency and lower emissions and lower water usage than conventional steam cycles. The STEP test operations are planned for this year, next, and going into 2026. So we've started up the facility and will be operating for the next 2-3 years. So a lot of valuable learnings already on design fabrication of those materials that go into this, and there's an opportunity for deep technology operations inside over the course of the operation. And if you want to keep up to date with the project, there's a website here that has a lot of information on the technology as well as the project. And with that, thank you very much. And I guess we'll come to questions later.
Completing in time, and second thing, you have given very nice presentation, and you have shown that CO2 is not always all time bad. It is also having good properties. Like at 74 bar, it comes in supercritical stage, so there no phase change is required. It can be utilized in storage, and it can be utilized in the good power efficiency can give the, so good, thank you. So now I call the next our speaker, Mr. John Kirchhoff. He is the co-founder and MD, co-founder of HP11. HP11 is an Australian company developing a commercially viable fusion energy technology that can be deployed worldwide. So, Andy.
So, good afternoon. Also, thank you for the organization committee to select us for this presentation, and I want to bring it a little bit closer to the future of energy that is potentially in fusion. So, yeah, the company is HP11 Energy. We are based in Australia, in Sydney, and basically what our approach is based is the energy that is created also in the sun, which then ultimately you could argue that most of the energy we use on this planet today is created from that process, which is a fusion process that fuses simple hydrogen into helium atoms. Just for the scale of the whole, to imagine that the sun is converting 4.2 million metric tons of hydrogen into helium every second. That is 38,000 septillion watts, about the energy of 91 billion megatons of TNT, and that is about the equivalent of 1.8 billion of the strongest thermonuclear bombs that were ignited on the Earth. So just for the scale, it's immense, and it's creating a lot of energy, and it's quite efficient at it as well. Here on this Earth, we have to use, we cannot use simple hydrogen to fuse into helium because we don't have the massive amounts of gravity that the sun has to compress this matter. So what we have to do, or what has been traditionally been done, is we use deuterium and tritium, which is the heavy isotopes of hydrogen. So, so what the classical approach is we use one deuterium and one tritium. We make it fuse in about 150 million degrees confined magnetic field, which is then releasing an alpha particle, a charged helium particle, and a fast neutron. And that neutron carries most of the energy, and then is somehow stopped and converted into heat, and then used for power generation. That's one way to do it, and there's a lot of effort worldwide going into this process. You probably, if you read anything about fusion, it's mostly the tokamak approach, which is a plasma ring of a magnetically confined plasma. And so basically what they do is they heat that plasma, they confine it in this magnetic field, and then they generate these neutrons. Most recently, the final campaign of the jet tokamak in England used that reaction, and they also they released some energy. What you can also do is, if you don't want the neutrons, because the neutrons they activate material and they also destroy material, so you can use a different reaction. And that is what we are focusing on at HP11, hence the name hydrogen and boron 11. And you can see that if you collide a simple normal hydrogen into a boron 11 nucleus, you can make them fuse into a carbon 12, and then they will immediately decay into 3 alpha particles that are charged particles, and there will be no primary neutrons generated in that reaction. So we get around all these problems of activating materials and also just destroying the reactor walls from the inside. If we get this process, if we can make it work, it solves a lot of the problems that we currently have, because as we know, the demand for global electricity or generally energy is also increasing exponentially. So we cannot, what we're currently doing in the Western world, we focus on renewable generation, and we know that this will not supply industrial-sized countries and will not be able to supply developing economies and also growing economies, which definitely need more energy than we have now. The problem with nuclear fission is, at the moment, we can build them, we can operate them. I think the safety is not a concern anymore, really. But the problem is the economies of scale that currently don't exist in the nuclear fission. You can make the calculation that if you want to power all of the world's energy with fission, you would need about 10,000 reactors, big ones. And if we want to do this by 2050, we have to build about 3 reactors every day. So that's about the scale of the problem. You can see that this is definitely not happening. Why we think our solution it could be part of the global energy mix for sure is we are globally deployable. We have no expectation of the location for the power plant. It could be anywhere. As we heard before, also the energy density is very high because it's nuclear energy. So the input material is very small. Just to give you an idea, the fuel pellet that we shoot every second or every 10 per second, they are only milligrams in size, and they release hundreds of kilowatt hours of energy per shot. So the amount of fuel that we need to put in is really, really small. Then boron, as you probably also know, is abundant. You can mine it in open pit mines in several locations in the planet, and it's also cheap. It's not something that needs special treatment or is toxic or radioactive. I think it's very safe material. And as I said, it's electronic, so we're not creating radioactive waste, and we don't have to store it or have all these other safety concerns that normally are very expensive and make the economics hard. So just to give you an idea about the people that we're working with, we have hundreds of years of experience in fusion and energy in general. Just to quickly run through them, Dimitri Vartanian is one of the most renowned inertial confinement fusion scientists in Europe. Eddie Patterson is from South Africa. He came out of the lithium-ion battery research and is now doing nuclear research in Australia. Peter Hoffmann is from Germany. He ran one of the biggest data facilities in Germany, is now working in China. Professor Vora is one of our co-founders. He's been working on proton boron basically since the 70s, and is basically the pioneer of the whole idea. Then we have Tom Milhorn and Max Tabak from the US. They are both also, Max Tabak is working in Livermore on the NIF facility, and Tom Milhorn was also working for the US Navy to evaluate fusion projects for the US military. Fabio Belloni is the head of the European Fusion Program at the European Commission. And Mike Campbell is basically the father of the National Ignition Facility in the US, which just recently announced that they got energy gain out of a deuterium-tritium reaction in a laser facility, which is huge for fusion in general. Big step. So what we have done at the company is because nobody really was looking at this proton boron fuel, everyone is pretty much focused on DT. We built the scientific capability to do experiments and also to develop theoretical and computational simulations for this proton boron fuel. We also did experiments, and we demonstrated that we can trigger reactions using a laser and on this fuel. Of course, the Q was only 0.1%, so we still have quite a way to go, but we know fundamentally the process works. Like I said, we modeled some conditions for the fusion burn of proton boron, which was long not really believed in by a lot of scientists. And we also working on a hybrid burn regime that is involving compression of the fuel as well. Via laser, you can also compress fuel. So that's why we call it the proton fast ignition approach. Our timeline is basically to adhere to the US National Academy of Sciences and Engineering and Medicine fusion report that they want to reach a decision to construct a prototype by 2029, and then develop the engineering and the rest of the plan basically by to start having a prototype in the 2030s. On the fuel physics, like I said, it can be ignited by a fusion powered the compressed target can be ignited by basically a spark that is generated by a laser. And currently we're optimizing that to increase the Q value basically of the whole thing. Just to give you a quick impression of how the reactor could look like, this is one reactor core that has the compression and the ignition lasers, and this is basically also coming to the topic of the session. This could be put in place of a coal power station and basically replace the burning of the coal power, and then using the heat to run the existing turbines and generate electricity to the grid that way. Thank you.
Thank you, Mr. Kirchhoff. So, Mr. Jan Kirchhoff given one good idea that everybody thinking of the solar energy and in the form of the wind energy, bioenergy, but he has given one idea that the source of the solar is the fusion energy. So why we cannot think about that? So he has given good concept that boron fusion is the concept which gives the good energy and good amount of energy. So he is working on that. So I think that is very good and it will be very required in the future. Thank you very much. Now I will call next our speaker, Mr. Suhas Bakshi, who is the founder and CEO with over 32 years of experience in manufacturing and software, and serves as the independent director of the board of Cryogenic Industry. So now I request Mr. Suhas Bakshi to kindly give a presentation on the biofuel circuit.
Good afternoon. This is a very, very interesting lineup. Geothermal, nuclear, and technology development happening around the world. What I'm going to speak about is probably not something which is linked to development of all new technology, but I'm going to speak about the picture that you see in front of you here. This picture is something which is very common for most of us who live in India. Post-harvest, when you go to any farm, what you see is a very large stash of agricultural residue. In India, we waste more than 235 million metric tons of agricultural residue. Now, across 10 states of India, if we think of harnessing this and convert it into energy, it could not only have a significant green energy impact, but it could also have a very strong social and economic impact in our country. So with this theme in mind, we started looking at why is it that this commonsensical approach of using this agricultural residue does not turn into reality. Okay? And when we looked at it, we essentially saw several strong reasons for it. One of the first reasons is the farm size in India is relatively small. The average farm size in India is around 2 acres. So if I have to gather 235 million metric tons of waste, I have to gather it over 100 million acres of land, and this would be owned by maybe 50 million farmers. So how do I go to 50 million farmers who are relatively unmechanized, relatively less automated, and gather this biomass and convert to energy? This clearly becomes a logistics problem to solve rather than anything else. So once again, the biomass availability is seasonal. The biomass is available for 2 months in a year, while the usage of that biomass, if it is in form of fuel, is going to be for 12 months in a year. Now this requires storage. Storage would require working capital. It will require capital for land and warehouses. What's the cost of that capital? Most of these small businesses are under the radar businesses whose cost of working capital is extremely high. This gets transferred to the cost of biomass, and that makes biomass relatively unattractive economically. Last, the customers of this biomass are companies such as NTPC or Hindustan Unilever or most of the large organized companies and their method of purchase is clearly driven by buying feedstock for reliable and quality production. It has processes which the rural folks, small rural businesses are unaware of, and thus there is a significant mismatch between what the buyer expects and what the seller is probably going to provide. And thus we came up with a solution which is a relatively different approach, and that approach is a digital platform. We said we will create a digital platform which on one hand will have a rural network. This rural network will have a mechanization fleet, warehouses, rural franchisees who actually do the job of aggregating biomass, and will have a direct farmer connect, making sure that the farmer is incentivized for participation. Almost everything is driven by economic necessity, and unless and until one is able to make farmer the stakeholder in this process, a lot of this aggregation is not going to become possible. So that was one step of our solution. The second step of our solution is creating a B2B marketplace, which allows the industrial buyers a clear visibility of at what price am I able to buy, what's the supply quality, what's the supply quantity, where is it available, can I buy it using my tools, which is RFPs, auctions, etc., etc. So how do we put this together and create an ecosystem which is going to get rural and industrial together is the problem that we looked at solving. And what we've ended up creating is, number one, something what we call as Biomass Bank. Biomass Bank is our rural network. It operates on a digital platform. This digital platform works in a cluster of 10 villages. It has company-owned warehouse, that is warehouse which is owned and operated by Biofuel Circle. It has IoT-enabled equipment sets, which would allow mechanization of aggregation to become possible. It has rural franchisees located in rural areas, creating economic and employment opportunities. It has a farmer who's directly participating using a farmer app, and all payments are happening on an online basis. So you create a digitally enabled ecosystem for harnessing rural biomass. What's the result? The result is rural area. A farmer who just makes biomass available is able to earn something out of just making that biomass available. He doesn't have to burn it. An aggregator who sets up a mechanization-driven aggregation business has a significant economic incentive available. And in addition to that, there is a labor component involved in warehouses who would generate income for themselves. So one is able to actually create an income incentive in rural areas, which is to the tune of around 1,500 rupees per metric ton, or around $20 a metric ton for those of us who are not from India. Now this is a significant economic incentive for participation. The second thing that we do is we create, once again on the same platform, a B2B e-commerce. The B2B e-commerce marketplace works like any other marketplace. So what do you have here? Here you would see a graph which shows demand and supply availability over a period of time. At what price is the buyer demanding biomass? At what price is the seller willing to sell biomass? At what price is the deal finally happening? What you clearly see here is an organized marketplace taking shape. You have a clear visibility of what's the price, what's the availability, when is the availability there, what's the volatility based on seasonality, everything that a matured market of commodity provides. That is what you have available as information. Now what happens when a marketplace like this exists? Investors are willing to invest in storages, investors are willing to invest in capacities and capacity creation. This is sign of a mature and an evolved marketplace actually having emerged. So together with the rural network, we've been actually able to create a very, very strong and sophisticated marketplace for biomass. What's our current status, current footprint? We are present in 5 states in India. We've got, I just go back a slide, yeah. We've got more than 20,000 farmers connected to our ecosystem. We've got 9 locations where we've got warehouses in these 5 states. More than 1,000 small businesses who are supplying on our platform, and more than 150 industrial and power businesses who are using our platform to buy their biomass. Together, we've so far transacted more than 500,000 metric tons of biomass on the platform in the last 2.5 years of existence, clearly aiding carbon neutral way of generating energy and consuming energy. We have plans to grow in states across India, so we would be present in 15 states across India by 2028. From current 5 states, we would probably look at harnessing biomass from more than 1 million farmers, which would still be 4% of the total farmers in India, and try to harness 10% of available biomass in India on our platform, and clearly become a catalyst for energy transition. We do have similar plans in countries outside of India. We do believe that continents such as South America, Africa, Southeast Asia, they do hold similar potential for harnessing rural biomass and bringing it for industrial end use. So in short, what we are trying to do is we are trying to kind of create a new era for bioenergy. I always feel that bioenergy, unlike other forms of renewable energy, can only be harnessed if it touches hands of people. Unless and until people are involved, unless and until people willingly participate, bioenergy won't be able to grow. And our platform, Biofuel Circle, does exactly that. It creates a mechanism for willing participation of people and harness bioenergy and convert it into a greener future. Thank you very much. Thanks for your attention.
Thank you, sir. So, we have seen that in India, agro biomass is very huge quantity it is available, and it's a problem for farmers that they wanted to get rid of, so they are burning. One problem, and second problem, as a power producer or as we need energy, because this biomass is considered as a carbon neutral. So we also want solution for the net zero or carbon reduction. But this is also solution. So basically, the demand is there, supply is there. So Mr. Bakshi has created a good platform which can people can use. With want demand and supply, this platform can meet the purpose of both the persons. Thank you very much. Now I call our next speaker, Mr. Rajesh Ayyappa Su, who is the director of GPS Renewable. GPS Renewable is the premier full-stack clean fuel technology company specializing in RNG, CBG, 2G ethanol and green hydrogen. And I request him to kindly present it.
Thank you so much. Thank you. Good afternoon. I represent GPS Renewables. We are a company based out of Bangalore. Just a brief that we have been around 12 years now in this line. Started with small biogas plants. When this subject was put us in terms of baseline power and process heat, we wouldn't fall under the category of baseline power in any case. So the focus is primarily on the process heat side of it, where the gas that is generated from organic waste, that utilization tends to happen in thermal areas and processing. During this period, we had won a lot of awards, but now in the past 3 years is when we have actually been capable of standing up in a forum like this and talking about the kind of capacity that can be built through large-scale implementation of organic waste to biogas and then on to bio-CNG. This is the pathway that we have. We have tried and put in a little bit of work in other biofuel areas, but as of now, the focus sharply remains on the area of converting agro waste, where we are completely in sync with Mr. Suhas Bakshi, because that we think is an area and which India as of now knows that this is an area that needs to be focused on. While we started with the smaller plants, where the focus has been on meeting regulatory norms through smaller units, and this small unit is what helped us develop the technology of online monitoring across many process parameters of a biogas unit. Biogas unit, as everybody knows, has been there for years and decades, but it is unfortunately dotted with failures across due to a specific reason of the lack of monitoring. This is what we have tried to achieve through a few patents that we have in terms of monitoring the biological health. The rest of it, because of that, there are many reasons why this becomes viable. Because we are not talking here about power. Power in this specific context is comparatively low financial value, while when we replace fossil fuel like LNG or LPG, the financial value goes up significantly. What we have, even in biogas, what have we done a little bit differently recently, and we have two units in operation right now in India. This is where we split a biogas plant into two across a wide geographical area. Processing happens separately at multiple locations, and gas generation happens separately at another location, where the customer needs green energy, but no customer will generate the quantum of waste that is generated in an urban setting to have the quantum of LPG or LNG or fossil fuel replacement. While at a different location, especially this is focused on residential areas, where waste processing is a challenge, but gas utilization remains. I mean, that's not something that they want to utilize. So we have a split system, which is called a distributed pre-digestion model, where multiple locations have waste processing and a single location has gas addition. This is a highly scalable model. Just some numbers. Okay. So a few advantages that this does not have to be supported by government land. It's very low land required. The waste processing person has very little capital to invest. The person who wants the green energy can pay, and the logistics, which is much less in this compared to the waste, which goes in trucks and hampers the traffic, that can be avoided by this specific system. I don't want to go into details because time is ticking. We have just showed a photograph of a model that we actually started off. This was started off pre-COVID, then COVID created many regular issues, but it was good for us because this is the time when we actually started getting funds, because people started getting into this space of sustainability. Just a brief at how this the space requirement of this specific unit compares to that of the solar power unit. Shows that at much smaller space requirement, we can generate, it's almost 20% of space required, we can generate equivalent power from this unit. This is the only area where we focus on power as an end use compared to a replacement of site. A few numbers. This 20 ton per day of a disparate model can generate. These are the basic numbers that are there. And the significant numbers that you look at is that if you convert it to power, and you know the cost of power in India, and conversion to LPG, you know the cost of LPG in India, it's very obvious that this specific system is suited for replacing the fossil fuel and not for power generation. Although this does work, I don't want to get into numbers. Then just in terms of the one that we had actually scaled up to a large extent and which has given a big traction to this particular space The cleanest city of India has the largest source segregated organic waste bio-CNG project in India. Government calls it in South Asia or in Indonesia. This system is presently operated by us. It was conceived, engineered, procured, developed, and operated by GPS, and subsequent. A few timelines were pretty critical in this case. We worked through COVID, the second wave, and completed the entire system and commissioning within a 11-month period. What this helps is not just to say that we have done it. The fact is that with this level of expertise that is right now, because we went on the ground and made our hands dirty, we learned the things that could go wrong in these kind of systems. We understand that we understand that have executed multiple plants now at similar time scales. A small picture gallery of what we have done. So what we have also been able to do because of this is to develop another product line where we have had to import products for upgradation of biogas to bio-CNG from outside. We have also developed a system where we can do this within India. With some of the technology has to be definitely imported, but the balance is done in India. This is the optimized range. And what this has helped is to presentation will end now, but the balance of it is very important. Is that if the paddy straw side of it, which is where the agro waste residue, the pollution, etc., has come into play recently, we have also started executing paddy straw to bio-CNG plant. The first plant which was executed was for Reliance. And this is expected to generate approximately 22 tons of bio-CNG on a daily basis. In terms of scale, we are looking to execute close to 14 such units. And in addition to it, there have been oil marketing companies who have been mandated to go ahead and put a significant portion of their resources into the biofuel space. And we have been sort of thankful that a couple of large OMCs have also gone ahead and given us the opportunity to go ahead and do this. We only hope that this is a very small portion of the entire market that is possible in India. The government wants to put 5,000 such units. We are looking at a few single double digits. So the main requirement in this case, and we have been trying hard to push, are the financial sectors, because they still are a little bit on the collateral-based lending side, which we hope will change in the future with more and more people understanding that this can have significant carbon footprint reduction potential, as well as a significant quantum of replacement of imports of natural gas for India. Thank you so much.
I think everybody understand that biofuel or bioenergy, CNG, very, very useful, specifically in the remote area where we cannot have the other energy source. So we can consider as a distributed renewable energy. And second importance is it can be reduce our carbon footprint. And third is it can reduce our foreign exchange. So this three aspects is very important to understand this biofuel, importance of biofuel. So now I will call our next speaker, Mr. Ranjit Manikar, as a versatile MBA professional and result-oriented digital media professional with 14 plus years of experience, and is now working for Entura Energy. So Entura Energy uses renewable energy electricity to heat block to solid carbon to glowing hot temperature is an insulated module. And then how we can convert from this stored energy to again power, I think we have to listen from Mr. Manjeet himself.
Thank you so much. First of all, thanks to the organizers for setting a beautiful stage for all of us. Few things I can promise you, mine won't be as long. I won't take the 10 minutes and it won't be very technical because I head operations for a company called Entura Energy. We're based in San Jose, California. We're in the news last week because we raised $150 million in Series B funding led by DCAR Partners, which is part of BlackRock. We're also backed by Breakthrough Ventures, which is Bill Gates' venture arm, and Lower Carbon, which is another big venture arm based in Texas here. So like I said, I had operations for this company. We are a pretty fast-growing startup in California right now. I've been there for a year now. I was employee number 40, and now we are around 98 or 99 people and growing really fast. The whole idea is that fossil fuel is being used across all of the industries, and it's a $1.1 trillion market, and there's carbon emissions which are going in the atmosphere. On the flip side of it, there is wind and solar, which is generated a lot, almost 25 terawatts in the US alone. And the biggest barrier for using wind and solar into industrial manufacturing is that it's intermittent. That intermittency is like the biggest problem we are trying to solve right now. And that's where Andorra comes in. Basically what this slide also talks about the same thing. We're saying industrial processes require reliable energy source. We have free and cheap, not free, cheap renewable energy sources, but the intermittency of it kind of is making it go to waste. There's a lot of wind and solar being generated which is not being used. And so that's our product in the middle. So what we're trying to do is take this intermittent source of solar and wind, store it in a thermal energy storage battery system. It's like a big battery. That's what we're building. What it does is it generates a clean, cheap, and reliable heat and power to the end users. Who are our end users? Right now we've commercially signed agreements with ethanol manufacturers. We are going to be generating heat for them, and the first projects are around 85 megawatts is what we've signed up for. The market is huge. We are in the first phase of what we want to do. We are generating heat up to 300 degrees centigrade to convert water to steam, and steam is what is going to be used. The company was started with the idea of taking solar and wind and converting it into electricity using thermo-photovoltaic cells, and that is still in progress. We are in the R&D phase, and the efficiency is around 25-30%, which doesn't make it a viable product yet, and we are going to be releasing that product hopefully for commercial use by 26 or 27. So with all this, the market share is huge. It's a $1 trillion market where we can, and internationalization is also not a problem because you can make this anywhere. The biggest problem we'll have to solve is how do you assemble these batteries, because each battery which we are developing is 16 feet long, 13 feet wide, 12 feet high. So it's like a truck basically, and it weighs around 64,000 tons. 64,000 pounds, sorry. The idea is like I said, it's very simple. It came from like graphitization furnaces. It's like a glorified heater. We have a heating element which heats up to 2200 degrees centigrade. This heat gets radiated to carbon blocks and graphite blocks, and graphite block stores all of this heat, and it's surrounded by rigid insulation. And using a throttle door, you kind of let the radiators stored heat into a heat transfer fluid, and heat transfer fluid takes it into the industrial process to convert water to steam. So that's where we got the idea, was from a graphitization furnace, and we've kind of taken it to the next level where we've proven the prototype, and it works. This is our core unit, which we have in Fresno, California, which is a functioning prototype which we use for basically all of our investment conversations. This converts intermittent solar and wind to heat, and we've been able to charge and discharge for more than a few thousand hours right now. This next picture just shows a cartoon of how an ethanol manufacturing plant will look like. The left side bottom is where all of our boxes will be, and if you look in the background, there's wind energy being generated. So the wind energy feeds into our thermal energy storage boxes, and then we convert that energy to heat, and heat is then provided to the plant. So that's the basic idea. Why am I in India? India has the biggest, out of the top 5 graphite producers in the world, India has the top 2. India has 2, and we're talking to both of them. So I am here more from a supply chain standpoint also, because India makes graphite, India has heat exchangers, and we need all of that for our mass production. We have taken on the challenge of vertically integrating manufacturing within our company, so that in itself is going to be a huge challenge. We just acquired a 50,000 square foot property in San Jose, which is going to be our pilot manufacturing, and like I said, we already have commercial agreements signed, and our first project should be commissioned by June of 2025. That's all. I mean, like I said, why are we using carbon or as a storage element? Because first, it's cheap, it's simple, it's scalable because a lot of people make it, so it's easy to find. There's enough capacity in the world for graphite and carbon. It's dense, so it stores a lot of energy, and it's also safe because we work it in an inert atmosphere, so it's not a problem, but even otherwise it's a safe element to work with. So yeah, that's all I have, and that's my presentation. Thanks.
Thank you, Ranjit. So the idea is very good idea that take the energy from sun and then capture that small sun for the night within the solution. Good idea, because everybody wants the energy in the night when off solar power. So I think it's good, and this will be the requirement for the future. So now I will take some question answer, 4 or 5 question answer. Quick, I request kindly ask very question and brief, so that it will not take much time.
We have this getting it on. It's on, but
Yeah,
1 second.
Yes.
Yeah, I just have a simple question. For the supercritical CO2 turbine, how you guys are managing the grid inertia part, as the RPM of the turbine is too high to be directly coupled to the grid. So what are you going to do for that?
Can you repeat question actually and ask slowly so that you can understand?
In your supercritical CO2 turbine, the RPM of the main rotor is very high. The best design I've seen is 10,000 RPM. That is too high for direct coupling to the main grid. So how you are providing that solution? Are you using a gearbox or an inverter solution for 60 Hertz electricity or 50 Hertz in case of a
It's very high, so what you are using? You are using some gear or something, how you control that speed? That speed requirement is very high.
Okay, so yes, the speed is designed Just closer.
Now we can.
So the turbine is designed for 29,000 RPMs. We are currently working through a commissioning program to actually get to that speed. So we're doing that carefully in stages. But it is coupled to a gearbox and to a generator.
Okay, next.
I have a question for Cora. So you said that you are storing energy in carbon blocks. What's the life of those blocks?
I don't need this, I can show. Our agreements are for 20 years. So the idea is that we agreement inside, if there can be replaced, we may not replace anything. So graphite is a 20-year lifetime is what we're saying.
Normally graphite as carbon would be difficult to heal, it's fragile. So how do you transport across different territories or different places?
That is why my life is miserable right now, because we are trying to, I also handle logistics for the company. So we are signing up with logistics providers who use flatbed trucks to move it from San Jose to, our customers are in the Midwest in the US, like Kansas and South Dakota and those places. So we are going to build a network of warehouses, retail warehouses and financial warehouses and provide take care of logistics and
Hello, my question is for Biofuel Circle. So does that digital platform currently or in future will also enable for some long-term contracts to procure those feed from the farms? Or is it just stop on like a trading, like if there is something available, I can buy now?
No, so obviously we look at even currently long-term contracts as well as spot contracts, if that's your question. So if you go to the platform today, you will have something like 200,000 metric tons of open quantity and delivery available from this month for the next 6 months. And 70 different forms of biofuel commodities, from a biomass perspective. So yeah, it's not just immediate availability, it is long-term contracts.
Okay. Yes. Cannot speak. Hear you?
Hello. I have one question for Mr. Rajiv, and thanks for the nice presentation. So you did mention the attractiveness of carbon as an energy storage engine. Now I'm jumping the gun. Now when it comes to stationary storage applications, how does this compare in terms of the rate at which the energy is can be dispensed off? I mean, the power rating and energy capacity scenario that you typically see in battery devices. How would you comment on how the carbon is?
Yes, carbon was also chosen from a techno-economic standpoint. So it's also a cheap element and it has a lifespan which works well for our projects. And it's also very dense. So those are the reasons carbon was chosen as a storage element. Does that answer your question? Yes. Yeah.
Okay, I think we can take one more question.
I have one question to James for geothermal energy. Any auxiliary power requirement for particularly generate geothermal energy, and any comparison between the wind, solar energy to geothermal energy, capital investment as well as operation part.
Okay, I think he talked him separately. And so can we conclude this session or anyone else? Okay, so let's conclude this session, and I thanks to our speakers, all speakers who have given their presentation within times. So thank you very much. Now I hand it over to organizers.
Thanks to all our speakers and of course our second chair. I'm going to request Rohan to step forward once again, and we'd like to just present to you a little token of appreciation along with this green memento with Rajnamo coming to you. Please remember us, and we'd like to share a blessing. this year. Thank you, ma'am. Thank you, Professor. While we have the mementos been given away, I'd like to take this moment to let you all know that we've arranged tea and coffee to spread close by on this side. You can please pick up your tea, coffee and come back to your seats because we're already running ahead of schedule. We'd like to be on time as much as we can, and that's probably one resource we're all struggling for. So please pick up a tea or a coffee and get back to your seats ASAP. Thank you, ladies and gentlemen. Our speakers are going to be around for a while, so in case you have any important questions, you can ask them while they are at the lounge. We have the scale lounge just opposite the conference hall. But at the same time, I want to remind you that the next session starts immediately, so please be back in your seats on time. Thank you.
उसका लेना